So in this topic, we'll be looking about overview and the type of bridges and what we do on conceptual design, what we do on design, detailed design, and also the process that are involved in a design of bridges, and also what are the future trends and how your career path would be looking like if you're choosing bridge engineering as your career path. So if we come to a brief overview, bridges has been there for a really long time. Bridges are generally built to connect 2 points over an obstacle. It could be a valley, it could be a highway, or it could be a railway line, and even to carry water from one point of origin to other locations. That has been done over a long period of time by use of aqueducts. And other than that, it's also a part of structural engineering. There are quite a lot of civil engineering disciplines that are involved in design of bridges. So that includes traffic engineering. In certain cases, hydraulic designers are also helping us. And in few cases, irrigation networks, they also help us. And it is not only a part of civil engineering. Quite a lot of other departments also help us generally in a fresh design, because we also carry quite a few pipes and also utility lines, electrical and those kind of work also happens in the bridges. So it's a very interdisciplinary work. Generally what design engineers do is. And so we also help in development of economy and community. So you can see quite a lot of NGOs are also involved in bridge engineering parts. So in Africa especially, and also in South America. So there is Engineers Without Borders and also Bridges to Prosperity. These are NGOs that are helping connecting rural communities across rivers, which become inaccessible in times of half a year or one-fourth of a year, and the people have to move a really long way around to get connected to the rest of their communities. And basically, coming back to the bridges, the oldest form of bridges are basically flexural or beam type bridges. So basically, timber logs or stones are used as just laid over the obstacle, like a small stream of water or things like that, since prehistoric time, just to cross them. So that will be that can be considered the start of the bridges. And after that, a detailed design thing came in as arches came in. So Romans started developing arches since very early times. So there are Roman aqueducts that are still dated up to 3rd century BC. That is, an aqueduct carries water from one point to their cities. So that has been done since 3rd century BC. And other than that, we can see root bridges, or we can say that cable bridges, that has been happening since very old times in Asia and also in rural South America. And similarly, bridges are also very effective in transporting aqueduct, I think, with arches. And with advent of technology, we can also see that new bridges also coming into effect, like cast iron. That came in around industrialization. It's around 300 years earlier. And also we can see steel bridges over the period of time in the last century, and also quite a lot of RC bridges, reinforced concrete bridges, pre-stressed bridges, and also in current scenario we can see a lot of FRP bridges, fiber reinforced polymers. So here you can see about the type of bridges over here, which I have mentioned. So these are old Roman aqueducts that has been here since at least 2000 years. And similarly, we can see the root bridges that are in part of India. So you can see it in northeastern part of the India. So the one on the right is the Millennium Bridge. It's a suspension cable bridge, but it's somewhat very futuristic, and it is in the heart of London. You can see that. So next, coming to the type of bridges, bridges can be classified based on materials and also their behavior, and also based on their purpose. So coming to materials, it's pretty basic. So you can say it is what kind of materials they are built on. It could be a steel bridge or a concrete bridge or a FRP bridge. So basically this is the basic type, but steel also you can see that there are quite a lot of other types of steel bridges. And similarly with concrete, based on the mechanism, you can see that it is pre-stressed bridges or reinforced bridges. And coming to behavior, so how a bridge behaves, you can see that based on compression, principle of compression, you can see that arch bridges behave in that way. It completely transfers forces through compression. On flexure, you can see slab bridges, beam or girder bridges, and also cantilever bridges. So they behave on the principle of bending and shear, basically you can say. And the third type would be tension bridges. So that would be the main mechanism in which they transfer their forces would be through tension that incur in their cables. That could be through cable stay bridges or suspension cable bridges. And the last type would be truss bridges. I hope most of you would be civil engineers, so you would know what a truss is. It generally is members that are completely released against bending. So it doesn't take any bending, it takes generally axial forces with that either tension or compression. That's how a truss generally works. And then coming upon the purpose, we can say it could be a footbridge, a railway bridge, a road bridge, or aqueduct. There are also quite a lot of other types of bridges where it could be used for utility bridges as well. So basically, these are the type of bridges which we could see. So here are the few types of bridges as we have discussed earlier. The one on the left is an arch bridge, and one at the center top is a steel girder bridge. One at the center is a simple culvert, which you can say it's a slab bridge. And one on the right is a truss bridge, and one at the bottom right is the Golden Gate Bridge, which is a suspension cable bridge. And one on the left is Signature Bridge in Delhi, which is a cable stay bridge. For fixing the bridges, it's quite interdisciplinary work. So you can say that the conceptual design of the bridge is a iterative process. It comes up with interacting with various departments. So basically, it comes a bridge is decided upon based on four things, you can see, as I have mentioned over here on the right. So one is the purpose, other one is the cost, then the aesthetics and the surrounding conditions. So purpose of the bridge, you can say that it is required for connecting 2 points across a river. If you want to make an interchange over a highway, or if you want to cross a railway bridge, existing railway track. So these are the purposes on which the bridge is built. Generally, the purpose is also not completely dependent on bridge engineers. That is the structural engineers, I mean. So in this case, there could be highway engineers who decide upon the level at which the road has to run. And similarly, if it is a railway bridge, it is dependent on the railway authority as well. And similarly, if it's a dependent engineering teams to decide upon the span of the bridge, where they are located. And similarly with a hydraulic engineer, if it's a navigable canal, then in that case, it is also dependent on the waterways, what is the clearance that should be allowed, and what is the intermittent spans, and where the piers should be placed, etc. So these things are decided upon based on the purpose of the bridge. And the next case would be the cost. Even though there could be multiple spans, multiple piers that could be placed on the way of the bridge, in certain cases the crossing which the bridge is built upon, it could be pretty deep. So in certain cases, they also cross across the oceans, or a small length of ocean. In certain cases, it could be somewhat pretty fast flowing rivers where putting multiple substructures would not be ideal. So in that case, it comes to a structural engineer to identify where to place the span. So whether it is ideal to place it on the edges only, or it is ideal to place multiple spans across the river. So that's how we come across the cost. The next thing is about the aesthetics. So certain bridges are placed in very important locations, like as I was mentioning in my previous image, it's about the Golden Gate Bridge in San Francisco, or a Millennium Bridge, or a Tower Bridge in London. Those kind of bridges are especially icons or landmarks. So they need to be beautiful. So the purpose of them is to serve as a landmark. So that is also dependent upon the architects who design the bridge. They are also involved, and they decide upon how the bridge should be looking and how it should represent the city. And the last one would be the surrounding conditions. As I mentioned in purpose somewhat, it's very interdependent. It could be based on the soil conditions, and it is also based on the type of the superstructure what we are carrying. For instance, in certain cases, certain type of bridges are preferred. uh, what I'm uh, what I'm trying to specifically say over here, surrounding conditions, is for instance, if it's a railway bridge, then you need a particular type of clearance that the rail doesn't intersect with your substructure. And similarly, if it's a waterway, then the ship or boat that is passing through under your bridge, that should not intersect with your bridge. It should be free to move across. And similar with the soil conditions, if the soil is somewhat pretty deep, the hardened soil is very deep, and very clayey or loose condition occurs over the uh, near the surface, then we have to put up very deep foundations. In that case, we tend to minimize the number of piers. So coming to the case of detailed design. So detailed design, people would think there are quite a lot of other methods which we design upon the forces. It could be based on various mechanisms, as we have discussed it earlier. It could be through compression, it could be through a truss, or it could be through other phenomena such as flexure. So in that case, people think it's pretty complex, and every forces are coming through different. We have to learn individual methods, and that is very important. Of course, it is important, but coming to the basics, they come upon from basically from the Newton's laws of actions. You can say that. So basically, we try to find out what are the forces acting in the bridge through this one. You can say every force has equal and opposite reactions. So basically, we tend to find out the reactions, and that's how we tend to equate the forces. So that is the first basic which we use for structural analysis. Let it be indeterminate structure or a determinate structure. This is the first thing that we try to apply over any stable to find the equilibrium. So let it be truss, let it be in the detailed design case, that's we tend to find the equilibrium. And this equilibrium is applied through various methods, either through finite element methods or through stiffness matrix methods, or even simple analysis as for a determinate structure, as in determinate structure. The second case would be how we find the forces. So the forces, basically everyone knows force is equal to mass into acceleration. So every let it be braking, let it be centrifugal forces, we tend to equate the gravitational for dead loads, we tend to put gravitational acceleration with the mass of each and based on various densities of materials. That's how we tend to find the forces. So that's how we come across statics, where we find the forces that is acting on the structure. And the third part would be where the structure stays in motion unless upon it is not disturbed by external forces. That's where the dynamics comes in. So whether it is due to the unstable forces of the wind where the bridge is in motion, and we have to find how, in cases this specifically happens in long span bridges where the bridge tends to aeroelastic or aerodynamically unstable. So there are various phenomena such as flutter, then torsional divergence, and those kind of things happen in long span bridges. So those things are find out using dynamics, and similarly for earthquake forces as well. So how we find the time period of the structure, and those kind of things basically occur with this. So that's how we determine the forces that are happening due to dynamics, due to the deflections and similar methods. Coming to design, we generally tend to analyze the bridges using, as I have mentioned in the fifth point, you can see we use various methods such as finite element analysis methods, stiffness matrix methods, flexibility methods, and similarly other simple methods are used for determinate structures. And further coming down, the design of the structure is basically done in limit state design for RCC structures. And when it's a steel girder, then we generally tend to go for either elastic, plastic, or buckling governed design. Coming to the design process, so first thing will be the geometry selection. So I think I have already covered this point pretty much. So first thing is based on the selection of the geometry and the material used. The first is the first step in the design. And so basically we tend to find out what kind of geometry we are going for. Either it is an arch or it's a cable stay bridge, and what kind of materials we are using for it. And they are pretty much interdependent in quite a few cases. For instance, we generally go for, if it's a tension based design, like a cable stay bridge, or if it's a suspension cable bridge, we generally go for steel in this kind of design. So they're pretty much interdependent. The span, as I have mentioned earlier, the span is not only the work of a structural engineer, but it's also dependent on the other field of engineering. As I have mentioned earlier, it could be due to the clearance of railways. So if you have two tracks running under the bridge, then we have a fixed clearance that we call it a 10 feet for one track, and mostly 20 feet or more than that. It depends on country to country. And similarly, if it's a highway, so it depends on the transport engineer. So whether we can place a pier in between the highway, or they want a continuous span, that also depends on them. So that's what I have mentioned in the next point as well. Transportation slash traffic engineers design on the alignment of the bridge as well. So it's not only what is happening under the bridge, even on the bridge, there could be certain curves, vertical curves, horizontal curves, how the bridge, the traffic moves on the bridge. That is also dependent on the transportation engineers in this case. And similarly, hydraulic engineers decide the clearance of the bridge, and they also pretty much help us with measuring the score depth, what is the velocity force that is acting on the piers, for instance. So it is pretty much dependent on the what is the volume of the water that is going under the bridge, that impact that causes the maximum force in the piers. And determining the maximum flood levels or the minimum flood levels, those things are also done by them. And the last one is the architects. They also play a very significant role in how they are made and how it is planned and where it is located, how it is made as a landmark, and for what, based on the purpose as well. So the bridges, you can the first basic things when we go for detailed design will be the evaluation of the permanent loads. It is somewhat very independent, very dependent on the, not only permanent loads, it is very dependent on the vehicle loads as well, because the amount of permanent load required is directly proportional to the amount of vehicle load that will be acting on the bridge. So in quite long span bridges, it can be pretty much noted that most of the bridges materials used are to satisfy for their own weights. Actually, it's used. They are just the materials used are pretty much used to carry their own weight. That is the basic thing. And Superimposed dead loads, they can vary. For instance, we have a veering court. In certain case, we have handrails if it's a pedestrian bridge, or we have vehicle restraint systems in case of highway bridge. And in case of railway loads, we have to also look into other cases such as ballast, or in certain cases it could be derailment. So those kind of forces also happen in permanent loads. But SIDL, that causes the ballast load, that will be coming into your permanent load. Other things would be the very important part would be the earth pressure. Quite a few bridges which you will be seeing, you might not even notice that these bridges are there, are culverts or integral bridges. These are very short span bridges. It could be up to 5 meters or 2 meters, etc. But these bridges are made as integral bridges. So what happens with them is that the earth pressure forms a pretty significant load on them. If it's a long span bridge, earth pressure acts only on the substructure. It doesn't much affect the superstructure. But in these kind of shorter span structure, they also form a significant part of the superstructure design. In certain cases, they act beneficial to our design because they induce compression on the slab or the girder in integral bridges. So this earth pressure provides additional compression. So these compression helps in benefit of design. So compression generally tends to increase the bending capacity of the structure up to a particular limit. So in that case, they are pretty useful. So we also estimate them in permanent load evaluation. So the last point, as I have mentioned, I think I have covered them already. So that is the handrails, then vehicle restraint system. In certain cases, there are also roofs in very aesthetic bridges. You can see they may be in certain important locations where you have like even shops and bars are located on certain kind of bridges where they have roofs. They not only act as bridge but also as a structure in this case. Then we are coming to vehicle loads. So vehicle loads are pretty important. This is what makes bridge engineering pretty complex. So coming to vehicle loads is what makes bridge engineering somewhat pretty interesting. Because in other kind of structures, we tend to take static loads. They are located in the same place over the period of time. Even though they have changes, it doesn't make much of a difference. But vehicle loads form a significant part of the bridge, which are located in different locations at different parts of time. So the analysis of vehicle loads is done using vehicle load analysis, moving load analysis, or also using or influence surface diagrams. So if an engineer is pretty competent about which part of the structures he has to give the reinforcements, then he uses the influence surface diagrams analysis, because they know that 1/4 of the bridge needs to be designed, half of the bridge needs to be designed, or across the slab, these are the locations which are the critical. So if I take influence lines for these locations and give those reinforcements or give those strength of steel in other parts of the bridge, then it is pretty good. So that's how vehicle loads are taken for design. Other thing is the moving load analysis. When people are somewhat not sure which part of the bridge incurs the significant major forces, then we also tend to go for moving load analysis. So simple vehicle load analysis, where the vehicle is placed at each and every point of the bridge, and the forces is also taken for the maximum envelopes. We call it the envelopes. When the vehicle is located at the start of the bridge, we would have a force at the particular point in the bridge. When the vehicle is placed at the end of the bridge, we will have particular force at the bridge, and we make an envelope of maximum forces for each location. So we design the bridges for these envelopes. So the same envelopes are also applied in influence lines, but we know those locations. So influence line can be very helpful in case you are pretty familiar with which part of the bridges you are going to be using for design, or if you're not familiar with it, the moving load analysis is pretty helpful. These loads are generally taken from, for India specifically, if I mention that, it's taken from IRC 6, and the type of vehicle loads we are using is IRC class AA or 70R in case of highway bridge design, and also in certain important municipalities where there is a high movement of vehicles and tanks that could be in border areas, if it's a significant city or things like that, then we use this kind of loading, that is class AA and class 70R. So class AA and 70R track vehicles are of same loads, but some class 70R is somewhat long and class AA is somewhat short in track vehicles. So they both are of only 700 kilonewton. In case of wheel vehicles, you can see that class 70R is somewhat heavy. It's 1000 kilonewton, but it's somewhat a pretty long load. So in case of a shorter design, in case of design of a shorter bridge, then class AA governs over here, because even though it's only 400 kilonewton, it is somewhat placed in a very concentrated area. Then even though we are designing the bridges for highway bridges for class 70 and class AA, any bridge is required to be designed for class A loading. So class A loading is applied for all permanent bridges actually. So class AA and 70R might be avoided in case of local municipalities or things somewhat not accessible by highway. If it's not a state highway or a major district road, then we don't need to use class 70 or class AA in those kind of bridges. It could be running to very few houses or a particular part of the community where this kind of heavy vehicles are not governing in those highways or the roads. So in that way, we'll be using class A for the design of those kind of bridges, and class B bridges. These are generally used only for timber. You can say that timber bridges, which are mostly not in use, but they are pretty helpful in case of temporary bridges where an existing bridge is broken, or in that case a subsidiary bridge is provided. So in that location, class B bridges, IRC class B comes into design. Class A and class B have pretty much the same pattern, but a variation in the magnitude of each and every forces, as you can see it in the next slide.